let me get this started. Can you clip this? This is just for the recording, not for the PA. So put that kind of like there, maybe, and then put this bad boy on your belt or something like that.
Try not to get tangled up.
Right. And then you've got like 15 feet of cable, so.
So I think a 15% tip is good enough for me. I don't think I need a point.
We'll beat the judge.
That's about this far over.
Thanks a lot for having me along. I'm John Rieffel. I'm currently a postdoc at Tufts University. Although I know at least 3 of these guys here from my days as a graduate student at Brandeis University. I'm not going to get into the pedigree too much, but it's nice to see some of you guys. For starters, raise your hand if you're a biologist. Oh,
come on, guys.
Okay, well, good enough. I might be sneaking some stuff past you, so it's good to know your audience. So I'm going to be talking about some ideas, some of which are my own and some of which are other people's, but all spring out of work that I've been doing over the past couple of years. And broadly, it's about this concept of mechanisms as minds. And I'm going to be talking a little bit about camping tents and caterpillars, and more broadly about the field of soft robotics, and how this notion of mechanism as mind ties into all of that. And if my punchlines are off, it's because my note slides are behind me. So I'll start by telling you the story about a caterpillar, which is not Eric Carl's Very Hungry Caterpillar, but it's a good place to start. I'm telling you about the Manduca sexa tobacco hornworm caterpillar, which is one of the world's most successful herbivores. At least caterpillars certainly are among the world's best herbivores. They eat several times their body mass in a day and stuff like that. The tobacco hornworm has been extensively researched because, as its name might suggest, it eats tobacco plants. And tobacco companies had a vested interest in finding out a lot about these animals, so there's a lot of research money. They became a kind of a second-tier model species. They're not Drosophila, they're not E. coli or C. elegans, right, or the lab rat. But there are labs all over the country and all over the world that study these caterpillars, which makes my life very convenient. And I'll give you an idea of what this caterpillar does most of the time when it's not sitting still eating a tobacco leaf. It's crawling around. And what you might see looking at the subtitles here is that it crawls the same, its gait is indistinguishable when it's crawling horizontally or vertically. It doesn't care whether it's crawling horizontally or vertically. In each case, you have this retrograde wave moving from the back to the front, and you can see it's kind of inching along, although it's not inching like an inchworm. It's important to know that several things that a caterpillar is not. A caterpillar is not a worm, and it's not a leech. And what we mean by that is that it doesn't have any circumferential muscles. So you can imagine how a worm moves by squeezing segments, and volume is conserved, and so the segments get longer, and then the worm inches forward, and then the segment compresses. Manduca doesn't work like that. For starters, it doesn't have any circumferential muscles. It only has mostly longitudinal muscles. And then it has a few muscles that go up and down. It's got 6 abdominal segments. That's what I'm going to pay the most attention to. And each segment has roughly 70 muscles in it. But oddly, each muscle is controlled by one neuron, just a single neuron. And there are no inhibitory motor neurons. And if you're not a biologist, you may not care, but for comparison, a cockroach, for instance, usually has dozens, at the very least, dozens of neurons per muscle, and often, and almost always has these inhibitory neurons. So, I it should be okay. Don't want to disrupt things. So the more we, and by we I mean the biomimetic devices lab at Tufts and the lab that studies Manduka at Tufts, the more we study this caterpillar, the more puzzled we become. Sort of, the more we learn we need to learn to be Rumsfeldian about it. So, for instance, we know that volume isn't conserved and pressure isn't conserved. First of all, the animal is full of these airways, these air tubes that bring air in and out of the body, so it doesn't breathe into lungs. It kind of has distributed lungs all throughout its skin. And these air tubes can compress during crawling. And then most of the animal is gut. And the gut is just a sack of goo, essentially. And that goo can swish around between segments. And in fact, we've taken some high-power X-rays at Lawrence Livermore, I think. One of these big high-energy photon sources. And looked at the animal while it's crawling, taking high-resolution X-rays. And you can see the gut swishing back and forth from segment to segment. And you can even see that the motion of the gut seems to precede any externally visible motion in the animal. So it's like throwing its gut forwards and then pulling the rest of the body forwards, which is kind of odd and not, you know, if you just look at this movie, there's, you know, you can't see the gut and there's no way that you can imagine that.
Do you know if that's part of its digestive system? The crawling is helping it digest by moving around?
I don't know, but that's certainly plausible. Other things to keep in mind is it has, when you're a completely soft animal, you have a lot of challenges. So you have some advantages, right? So you have a very large workspace, and you have multiple degrees of freedom, which is great because you can reach almost anywhere you want to. But unlike the kind of mechanics that you'd see in a normal, like a human skeleton or mammalian skeleton, there are no muscles in opposition. So when I go like this, I have a muscle that'll pull my arm back in the opposite direction, and the caterpillar doesn't have that. It doesn't have sort of pairs of muscles in opposition. And the only way it can regain its shape is because the body wall itself is under tension the whole time. And if you were to release the tension, say bleed the gut out of the animal gets shorter and it contracts and it can't crawl. And it has to sit there and wait and build up body pressure again and build this pre-stress into the wall again before it can crawl, which is very interesting. And the real question that we are asking ourselves is how does it manage to control such a complex body and such complex physiology with such rudimentary neural architecture? It's really got, its body is way more complex than we think it should be able, than its brain is much too simple, we think, to control its rather complex architecture. And it turns out that, well, I'll get to that a little bit later. It's something to keep in the back of your mind. But what we're really interested in is the Manduka sextet as a prototype for a completely soft robot. You might recognize the soft robot in the top slides here. The military, for instance, has a very deep interest in soft robots. You know, something that can take one shape and then melt, flow through a hole, and reconstitute itself on the far side of the hole. Although we're quick to emphasize that there are a lot of biomedical applications for completely soft robots too. Everything from surgery to endoscopy, any number of things that they can be solved by a soft robot much more comfortably than they can be solved by a more rigid robot.
Not being funded by Skynet.
No, we're not being funded by Skynet. We're just being funded by DARPA. So, or I should say, we're being funded by Garmin, so you can answer your own question. But
So when you say that you're working towards one of these soft robots, do you mean the same kind of constraints, that is, not having muscles in opposition?
In a large part, yes. So a lot of that comes from just the constraints of building a soft robot. If you have a rigid-bodied robot, then you can have levers. You can have joints, and muscles acting in opposition makes sense. But when you're completely soft, there's nothing really to pull against. And really the best way to get a restorative force is through body wall tension. So we want to build a soft robot that is modeled on the Manduka, which is great because it means we've got a working prototype. And there are several other groups that are also trying to build a soft robot. None of them have working prototypes. So they're trying to engineer up a working prototype, and we're trying to reverse engineer a working prototype. So we've got something that works, but we don't know how it works. So we're trying to figure out how it works. But we do know a couple of things. We do know that a soft robot like the Manduka is going to be under control. So it's got way fewer muscles than it has degrees of freedom. It's also similarly going to be under-actuated. Well, the first is that it has control over fewer degrees of freedom than it has. That's under control. Under-actuated is that it has fewer actuators. And it's going to be underpowered. So you can't just stick a 24-volt car battery in your Caterpillar and have it still be soft. You're going to be severely power limited. And so we'd really like to know how the Caterpillar does it, because if the Caterpillar can do it, then we're hoping our soft robot can do it too. And so this brings to focus the idea of mechanisms as minds. And really, it's the idea of, maybe our brains aren't as smart as we give them credit for. Certainly maybe the Caterpillar's brain isn't as smart as we want to give it credit for. And instead our bodies are much smarter than we give them credit for. And you see a lot of this in the natural world. The Manduka sexta caterpillar certainly isn't a revelation in this regard. So cockroaches, for instance, they have muscles which, depending upon when they're used, can act either as actuators or as dampers. So they can act as shock absorbers. Wallabies, kind of kangaroo-like animal, they use the same bouncing gait to hop along on a flat surface as they do to hop along an incline. And the only thing they change is the length of one tendon in each leg. So this is a broader term is morphological computation.
I'm okay for
this is a way of outsourcing a control task that normally you'd use neural architecture for and putting it directly into the body. So if all you have to care about when you're climbing a hill is the length of one muscle, that offloads a whole lot of computation. Takes it out of the brain and puts it into the body. And that's our working hypothesis about how the Manduka does it. And we're beginning to get some convincing data that, in fact, that's true. But I'm here more to talk about how, if we suppose that's true, how we can make a soft robot move. And can we make it move using the same principles? So I'll give you some examples of this phenomenon of mechanism as mind operating on much simpler systems, but still mechanically complex systems. So the first one I want to talk about is tensegrities. If you've ever set up a self-standing camping tent, then you're familiar with the idea of a tensegrity. If you have a kid under the age of 5, they probably have a toy at home that's a tensegrity. And if you don't, you'll probably get one as a present for your kids soon, because they're very popular. So the idea of a tensegrity is you have a bunch of rods, which are rigid, and a bunch of elastic strings. And in the structure, the rods are always under pure compression, and the strings are under pure tension. And no rods are physically connected to other rods except through strings. And it's a very queer kind of structure if you look at it at first, because they don't look like they should be able to stand upright, but in fact they do. And it's because of this synergy between compression and tension that all the forces are lined up just right. And you have these really great properties. For instance, if you loosen all the strings, the tensegrity will collapse, which makes them very popular in space applications. For instance, if you want a mast to go up on your satellite or an antenna, it's almost like origami, where you send up this bundle of rods with some strings, and you pull a string once you're in space, and the tensegrity deploys, and so they can be packed away very compactly. And they have this tight mechanical coupling that's brought about by this pre-stress stability. And what I mean by that is, if you wiggle any end of the tensegrity, it's distributed all throughout the structure. And if you wiggle one rod, every other rod in the structure senses that wiggle. And that particular aspect, that dynamical coupling, is going to come into play with what I'm about to show you. So, are you guys familiar with GAs and evolutionary algorithms? Good, because I'll skip over this. I just have some canned slides, but this all looks familiar, right? We've got evolutionary algorithms. So I'm going to use evolutionary algorithms to evolve the controllers for tensegrity robots. Here's a picture of a 4-bar tensegrity robot we built at Cornell. As you can see, it's got a single servo on each end of each rod. So 4 bars, 8 controllers, and I think it has 32 strings. I could be wrong about that. It's got quite a number of strings. Obviously, only 8 of those 32 strings are controlled.
So the strings control of the rods are?
Right now it's the strings. So it's rotary servos. And I think I have a movie of a 3-bar tensegrity. Oops, let's go back. And you can see one interesting aspect of tensegrity robots, which is you press a button and you can deploy them, which is great. And when I went to show this to our funding agency, they were very impressed when I pulled the tensegrity robot out and spent 15 minutes untangling all of the wires and then pressed the button. But it was in a poster tube, so it was impressive. And I pressed the button and it deployed. And in fact, you can make these things move if you are able to kind of exploit the resonant frequency a little bit. And if we were to wait long enough, you'd see that this robot is going to creep towards the right. And this was a controller that I evolved in simulation and then transferred to the real robot, but it's a centralized controller that's sending commands to all the servos, which works great on a 3-bar tensegrity, but what we're really interested in is much bigger tensegrities. So this is, I'm going to show you a family of tensegrities that I can create using work that I'm not really going to discuss here, beyond saying that I have a way to grow very large tensegrity towers that all look like each other. There's an underlying grammar. I'm happy to discuss this afterwards if you want to see it. So I have a set of rules that can turn this tensegrity into this tensegrity, into this tensegrity, into this tensegrity, into this tensegrity, and my computer runs out of RAM if I try to grow it any bigger. Or actually, it just slows to a crawl. So really, I want to control tensegrities like this, these big, massively complex, dynamically coupled systems. And it's pretty clear that you don't really want to use centralized control. Centralized control works great when you have 3 or 4 or 8 actuators. But we're talking about 15 bars. So if you put an actuator on each end, that's 30 strings that are getting actuated out of the almost 80 strings that are in the structure. And particularly if you're running control wires back and forth, and if you're trying to feed all of this data back into a centralized brain, we have a term for this. Spaghetti, which is, it's a real mess. It's enough of a mess trying to build a 4-bar tensor. And the idea of putting a centralized controller in a 15-bar tensegrity robot just gives you the heebie-jeebies. So there's got to be an alternative. And the alternative I came up with is a completely decentralized controller. So let's make each strut in the tensegrity completely autonomous. And I'm going to put inside of each strut a spiking neural network. spiking neural networks are very similar to regular neural networks, but they can adjust their firing rate. So regular neural network fires every time you update the neural network. You give it some inputs, it calculates the sigmoid and spits an output. A spiking neural network has kind of a buffer that it builds up, and it sends zero, it sends nothing to its output until it's calculated enough inputs over enough time that they pass a threshold, and then it spikes, it fires once, it drops its counter back down to zero, and starts reading inputs. And what's important about this is if you have, in this case, 15 spiking neural networks in the structure, they can all be firing at different rates. And you don't have to worry about hand-tuning firing rate of your neural network to exploit the resonances of the structure. You can hope that each spiking neural network can on its own discover the resonance at its particular location. And so there are no extra wires. Each module is self-contained. And more importantly, there's no central clock, like I said. So they can find their own timings, which is very useful. So what I'm going to do is I'm going to evolve the weights on these 15 neural networks. And I'm going to select them for distance traveled. So this is like almost any other A-life mobile robotics presentation you've seen, right? I'm trying to make it move. Everyone's been doing that since Carl Sims. And here you go. You see the structure. This is simulated in ODE, the Open Dynamics engine, which is a pretty good physics engine for what it does and for the price. The red ball you see over there is the center of mass, translated upwards just so you can see it. And you can see that the structure is vibrating and that it's inching forwards. And I don't have a laser pointer, but what's particularly interesting is there are really only 2 or 3 strings that are doing all the work.
What are the inputs?
So the inputs, so there are 15 modules, each with an independent neural network. Each neural network has 2 inputs, one for the tension of one string on each end. It feeds those through the hidden layers and stuff like that, and then 2 outputs, and the outputs are the rest lengths of those same 2 strings. So, and it's really only, it's binary, on or off. So it can basically either say your rest length is L or L over 2.
There are sometimes multiple strings out of one.
Yes, so each, in order to be stable in 3 dimensions, each element has to have at least 3 strings attached to it on each end. So there's actually also a meta evolution I'm running, which is selecting for which strings you pull. But you can only pull 1 string on each end. And that comes out of the limitations of the servos we're using and just sort of what we wanted to build, because a servo can only pull 1 string. It's really hard to put more than 1 servo on the end of one rod.
Right.
But you don't necessarily know a priori which string you want to
You
pull.
could pull all of them at the same time.
You could pull all of them at the same time. But it's not as easy as it sounds.
And did you evolve this to try to achieve that motion? Is that what
All I told it to do was move. So the only way it could move is by inching forward, and the most efficient way it can move is by exploiting this resonance, this dynamical coupling. So you can see this is probably illegible on this, but this is the string activation. So this is the outputs of all the neural networks. And you can see there are really only 2 in this case that are doing all of the work. And they're firing at different rates. Yeah, they're firing at different tempos.
Yeah.
So there are different resonances at different parts of the structure. And they're a little chaotic, but they're definitely rhythmic, right?
Yeah.
And so it's really 2 actuators in this. It's 2 strings in the 78-string structure that are making the whole thing move. And the only way to do that is by exploiting the dynamics of the structure. So the question is, how tightly is this gait, is this movement coupled to the dynamics of the structure? And what we can do is we can play with the timing of the gait. So I'm going to take the output of the neural network, which is just on, off, and I'm going to take all 30 values and kind of save it as a script, as a macro. I turned on at this point, I turned off at this point, and I'm going to double it, and I'm going to have it, and I'll double it, I'll triple it, I'll quadruple it, so the rate at which things are pulling. Then I'll have it and stuff like that. What I'm looking for is speed and variance. So what I mean by that is, if you look at how a bicycle moves, it moves very much the same regardless of how quickly the wheel is spinning. Which is to say, over the course of 5 rotations, it moves the same distance, regardless of whether, modulo skidding and stuff like that, regardless of whether it's moving at 1 RPM or 20 RPM, right? And more importantly, when you pedal fast forward, your bike doesn't veer to the right or veer to the left, right? So the dynamics and the controller are pretty well separated. And so what you'd expect, if this evolved controller weren't tightly tuned to the dynamics, you'd expect that as you change the speed, nothing much would happen. Nothing much different would happen. But in fact, this takes a while to load. What you're looking at is from above, this is the ground plane, the XY axis. This is the movement of the center of mass. Blue there is the nominal motion, so that the gait it was evolved at. You can see it moves at a pretty good clip. And as we make it move slower and slower, as we slow down the gait, not only does it change the distance traveled, but at some point there's a phase shift, right? At some point it starts walking in the opposite direction. And to be fair here, you can see that as I slow it down, it seems to move further. And that's because I'm running it for a fixed number of steps, if you will, not a fixed number of simulation time steps. So I have to let the simulator run longer. So there's a point at which I'm running the simulator so long that it makes one motion, then it can kind of skid along for a little bit. So this is normalized for number of steps, not for sort of total time. So these gates you see on the bottom take much, much, much longer to happen. But the real interesting thing is the phase shift, that at some point you're walking slower, but you're walking in the opposite direction, even though you're just taking one step after another. And you can speed it up, and the same kind of thing happens. And this is really a really good demonstration of how the gait that I've evolved is tightly coupled to the dynamics of the system. And I think I have some other results here. And you can see here, it's even worse. There are points where if I try to speed the gait up a little, it just falls over. The whole structure just falls over, and it can't do anything. So it's not a very robust gait. But really what's happening is it's walking a tightrope. It's figured out the one set of dynamical actions that it can perform to move very efficiently across space. But the second you mess with the timing, it falls over. But what I was really interested in is how well these neural networks were talking to one another. Did they just happen to find the right pattern that they could all move at, and they weren't really communicating with each other? Well, there's no explicit communication, right? But the idea is maybe they could be sending signals back and forth just through the change in tension. Because remember, because of pre-stress coupling, any change you make in the length of one string is propagated throughout the structure. So what I can do is I can turn the neural networks back on, and I can run the neural networks, and midway through a gate, I can addle one. I can turn it off so that it's not sending any outputs anymore. And what I want to see is how that affects the other gates. Sorry, how that affects the other neurons. So if there's no communication between these controllers, then turning off one controller should have no effect on the other controller. Right? In that case, the null hypothesis, right, is that all these controllers evolved independently and they're all doing their own thing, but they just got lucky. Right? They're acting in concert, but they're not really collaborating with each other. But as you'll see, so I'll mute the one on top. You can see halfway through, and it's not too clear in the slide, but the second controller, which is at the far end of the structure, starts firing faster. And so it's gotten some kind of mechanical feedback from just because the dynamics of the structure have changed all of a sudden. And so it starts behaving differently. And here's another example where if you make one stop, then the other one stops too. And more importantly, when you start the first one, the second one starts again too. So here's this idea of morphological communication. It's the idea that you have these completely autonomous controllers, but they can send information back and forth just using the body itself as a data bus, as an information conduit. And that's really, really clever, I think really important when you're talking about this idea of mechanism as nonlinear. So back to soft robots, right? We know they're going to be under-actuated, under-powered, and under-controlled. And I've given you one idea of how you can make such a system move with a sort of a minimum of neural control. So now I'm going to talk a little bit about the soft robot that we're building. What you see here is a 6-segment body that is made out of silicone elastomer, so it's rubbery. It's self-supporting, and it's got some of this pre-stress built into the wall, so if you crumple it, it resumes its shape. And we're actuating it using nitinol wires, using memory wires. And what's nice is you get a lot of things kind of for free just by using a body shape like this. So this is a finite element analysis model of half of the body. And you can see what's happening here. This is a colleague of mine who did this. I'll try to play it again. She's just pushing from the back. She's just applying a force to the back, and you get this retrograde wave that moves just because of the properties, the elastic properties of the system. So what I've done is I've taken a 3D model of this, designed by our mechanical engineers, and I've inputted into the physics engine, which was created by NVIDIA, the graphics card company. It's actually created by a separate company that NVIDIA bought. And it's not open source, but it's free to develop for. And particularly when you turn on hardware acceleration using the GPUs found in NVIDIA graphics cards, you get a pretty significant speed boost. I saw 2 times. I was just talking to someone who says, "Oh yeah, we get 15 times by turning on hardware emulation." So hardware acceleration is nice. So I'm going to use spiking neural networks again, our good old friends. It's a little more complex now. If you look at 2 segments connected by muscles here, from the side, let's pay attention to the blue muscle. Now it's going to get input from its 3 neighbors as well as itself, and it's going to use that information to control that one muscle. So we have 4 inputs, 1 output, but there are 5 muscles on the bottom and 5 muscles on the top for each side, so there are 20 muscles total. And again, we're going to use these independent networks. And again, fitness is just positive distance traveled by the leading vertex of the soft body.
Are the muscles segmented, or do they go to the length of the thing?
Each muscle connects between 2 segments.
Okay.
The midpoint of one segment on one side to the midpoint of the next segment.
Is the feedback always in one direction?
There's no feedback per se.
Inputs from segment to segment. Is it is it a feed-forward neural network?
There's no feedback between segments.
Okay.
So
it's just within one segment.
Yeah.
Okay.
Or I should say within one intersegmental ring, if you will. So,
Gotcha.
right, because muscles aren't within a segment, they're between segments. So, between the first and second segment, you have a set of muscles, and those muscles talk to each other, but they don't talk to any of the other muscles in any of the other segments.
Gotcha.
So there's a little bit more communication, but not a lot more communication.
The sensors are the tensions and voltage and before plus.
So now I'm looking at the distance between the 2 vertices, and that's the input, and then the output is on or off And when you're on, again, you pull. And right now I have a strain of, I think, still 50%, which is much higher than you get with nitinol wires, but for now it's good enough for this. And this is the kind of thing I get out. So again, the red line on the top is movement of the leading vertex, and you can see that in the first few cycles it's moved backwards. And that's actually makes it a little tough for evolution because it means almost all gates initially move backwards. And so you've got to work yourself out of that hole when you're trying to evolve locomotion.
Needs to figure out which end is the front and the back.
Yeah, well, that's part of it, right? And so what you're going to see, and the movie's a little slower, but it's actually got a retrograde wave. You can see this wave propagating from the back of the structure to the front of the structure. But at the same, and you can see that many of the segments are lifting. So now the rear segment, second segment, third segment, fourth segment lifts. And again, this is just what we're getting for free out of the dynamics of the system. And at some point, I'm going to show you the other side to see that muscles over there are pulling too. But the other interesting thing is I haven't enforced any bilateral symmetry. And as a result, you can see that it's actually got a bipedal gait happening on the back. So it's actually walking. And then again, it's the bipedal gait is reflected in the front too. So it's walking with its back legs and walking with its front legs, and just using the middle legs really for friction. And this was pretty cool. I got this, I think, the day before Thanksgiving. So,
Nice.
That's really where my analysis ends, but you can see where it's headed, right? And you can see how you can use this really simple neural architecture to control really complex systems. And so there's hope for soft robotics. There's hope for controlling a system with so many degrees of freedom using relatively simple neural commands. And that hope resides in this idea of mechanism as mind, morphological computation, of taking some of the control tasks that you'd otherwise devote brain power to and instead embed them directly into the mechanics of the structure. So what I'm going to be doing in the coming weeks and months is tuning the parameters for the physical robot. So right now it's an imaginary robot, but we have a real robot, and we can put it in biaxial testers, and we can do very accurate finite element modeling of this thing. And we want our reduced order model, which is phys-x, to match the physical robot as closely as possible. That way we can evolve things in simulation and transfer them to the real animal. Ultimately, we're probably going to have to use some kind of tiered simulation where we use a low-resolution phys-x model and then a high-resolution phys-x model, and then abacus or another finite element system to come up with a really good controller, even though it's computationally very intensive, and then put it in the physical robot. And ideally, of course, we could use kind of ideas that Anthony here wants in coevolution to simultaneously evolve the accuracy of a simulator and the controller for a robot. And that's work that Hud Lipson and Josh Bongard did, and it's really neat stuff. So that's it.
Any questions you want?
Yeah.
Fire away.
On this one, the soft bodies were 1 year. You were only evolving the...
I was, again, evolving spiking neural networks, and the only parameter I was changing was the weights of the spiking neural networks.
So no evolution of the structure.
No evolution of the structure.
Mechanical properties of the structure and so on.
No, right now, for starters, it's just trying to find the best neural controller for the structure.
Yeah.
Ultimately, I think I see where you're going here. Ultimately, probably what you want to do is you want to co-evolve the mechanical properties as well as the neural properties.
Yeah.
And we've written a couple of grants about how we go about doing just that.
Yeah.
But it is a really interesting question to ask. You know, if you can evolve in two directions, one is making your controller more complex, and one is making your body more complex. Which way do you want to go? And does making your body more complex necessitate making your brain more complex too? I think I've given an example of how sometimes you can make your body more complex and get and sort of get something for free without needing to add much neural overhead.
Yeah. So yes, because this, especially this movie, really begs the question about the optimality of that body. It looks far from optimal.
Yes, it is far from optimal. But keep in mind, we have to give a product to DARPA at some point.
Yeah.
And so I'm interacting with mechanical engineers and electrical engineers and biologists. I'm a computer scientist. But they're not happy if I say, build this, I came up with a new design for your robot, right? Can you build this? Can you make new molds and stuff like that? So we need to work on the workflow to make that kind of thing happen. But you're absolutely right. If we want a soft robot that can move as efficiently as possible, then we really do need to evolve the morphology as well as the control.
Yeah, it also, evolving the morphology fits in so well with your presentation. I was really looking for.
Yeah, and I'd really like to do that. Right now, it runs up against the limits of physics, of the physics engine we're using, because it's representing the soft body as a tetrahedral mesh, so a bunch of pyramids connected together, and you have a single number that determines the stiffness between any two nodes and the damping between any two nodes, but it's a single number for the whole soft body. So you can't tune those parameters on a second-by-second basis, or even on a tetrahedron by tetrahedron basis. It's just one number, right? And what I'm doing now actually is getting those two numbers, the stiffness and the damping, to match the physical properties of the elastomer we're using.
Yeah, but already I can see how just the thickness of the rubber, the size of the segment, the diameter.
It all comes into play.
And you can change while maintaining a uniform sort of segment unit.
So but you need to do body-brain co-evolution, right? It's not you can't evolve the body without evolving the controller for it, and you can't evolve the controller without evolving the body for it. And so it's an interesting problem. It's a challenging problem, and it's what I'm beginning to tackle right now. But I'm going to have to rewrite a lot of my code to use the CUDA architecture instead of physics.
So you mentioned that the caterpillar has 70 muscles in each segment. Yours has 4.
Yes.
So any thoughts on how those, changing the number of muscles will affect things both when you can evolve?
So just in terms of raw computational problem, the more muscles you have, the more neurons you have, the larger your search space is for evolution. So it's a harder problem. Also, it's an engineering problem. Right now, it's hard enough, believe it or not, getting 20 actuators into a soft-bodied robot. And there's no, I can't see in the next 10 years getting 70 muscles per segment into a soft robot. But a lot of those we don't need. It uses some of them to, it has these grippers that are actually passively grip, and you have to pull a muscle in order to get them to unlatch. So this robot, for instance, doesn't have any of those yet. But if we did add grippers, and we want to add grippers, there we need to add at least 2 more muscles per segment. So it does begin to balloon up, and it is a question. It is another question.
Could you simplify the evolution by doing something similar to what the centipede millipede seem to do, which is to have basically the same program in each segment, except perhaps the head and the tail segment, and thereby simplify your search space?
You could, but from what we know of the caterpillar, that's not what it does.
Yeah.
And it's not clear that it would work in a soft robot too. So it's not clear that you want the middle segment doing the same thing as the adjacent segment. And you have to make a lot of assumptions if you want it to be done.
Yeah, I mean, clearly the phase it's quite different. It can be.
But it's that's also worth exploring.
Yeah.
Because then you could, it'd be interesting to see whether you could use the same controller for a 4-segment as a 40-segment robot. I haven't thought about that a lot, but it is worth exploring.
So, how nicely convergent are these neural nets? Do you have to run them a whole bunch of times before you get a solution? Do the solutions always end up the same?
No and no.
Okay.
So I've only been able to run half a dozen runs or so. So I didn't get a lot done over Thanksgiving weekend, but every solution has been different. It's had a different fitness. And from what I've looked at of the movies, all the solutions coarsely look different, but you do tend to see these retrograde waves, which is a good sign. It's a good sign that that it's an obvious or relatively wide evolutionary target, an evolutionary solution to have to exploit this pre-stress, body wall pre-stress in order to create retrograde waves.
Have you tried a hand human-tuned version?
No.
All right. The John Henry approach?
No. Partly because it's anathema to us, A-life types. But also because I wouldn't really know where to start. I mean, you sit there with 20 buttons, one for each controller, and do on, off. I mean, we've tried for a much simpler robot, and even then, it's very hard. It's very hard to figure out. And we have a separate robot that a master student is working on right now that's activated by hydraulic pistons and pneumatic pistons. And he evolved a controller for it, and he was able to do what none of the mechanical engineers were able to do, which is make this soft robot move. But it doesn't move the way you'd think it should move, or the solution he came up with through evolution isn't the kind of solution you'd expect, if you did it by hand. So this ties into a lot of what John Koza says about evolutionary algorithms, right? That they operate orthogonal to human thought, and that's the real advantage in their ability, to quote Koza, as an automated invention machine, right? They can come up with solutions that are more clever than solutions we come up with, but only if we unfetter them from our human assumptions. So the less domain knowledge and the less expert knowledge we put into an evolutionary system, the more interesting the results we get out of it.
Right. I think it was Crick who said evolution is more clever than you.
I have that as Orgel's second rule.
Okay.
Crick is quoting a colleague, but yes, that's on my webpage.
Cool.
Keep going.
Cool. Did I answer your question?
Yeah. So have you gotten a robot to walk yet? One of the Tensobots or?
We have a 4-bar tensor that works, but that was at Cornell, and I'm now at Tufts, and our funding at Cornell doesn't exist anymore, so as blow the winds of fate, so blow the winds of tensority robots. There's no money in it. But I'm confident
I'm visualizing a huge market in the camping field.
Yeah.
If the tent followed you along.
Sure, yeah.
And then just popped itself open.
Well, I mean, there's a lot of demand in space structures. So most of the publications in technologies these days are in space applications. I think your tent would get a lot heavier if it had motors in it.
But if it walked itself.
Yeah, who cares how heavy?
Yeah.
But it'd probably have to graze for food along the way.
There's an existing art solution.
Yeah, just wait for insects to come in and then it just uses that as fuel.
If you give your tent a digestive tract, I am not sleeping in it.
I'll write a white paper for REI.
So John, one of the things I remember Barry saying about that caterpillar that was pretty fascinating was that its central nervous system doesn't change as it grows.
Yeah, so
From
it uses
little
this,
tiny up to
it uses the same controller as a hatchling that it uses as a full-grown adult, more or less.
so. I was curious if you have any plans to try that in software.
So right now, PhysX is unitless, so I can say it works the same on a robot the size of a penny as it does the robot the size of a skyscraper. But there's no.
Well, I think the craft is scaling in a weird way.
Well, no, because with the rubber, you have to change the properties.
But because I
Certain
yeah,
size is gonna.
I get a faster computer and things move twice as fast, but they're not moving twice as fast because my solutions are
Unless you're willing to put more triangles into your structure,
Exactly,
which
yeah.
is a structure twice as big.
But I think right now your solutions are very tightly coupled to the actual size of the segment. Because physical properties too.
Right. Well, it could be that the physical properties scale the same way that the controller scales as the caterpillar grows.
Is that true?
I don't know. Nobody knows. But keep in mind.
You didn't think that very small, right? The tension is going to be a lot bigger.
Yeah, right. We have. I mean, it's very hard to study these things because the caterpillar itself, because it's soft and it's a big squishy bag of goo. You cut it open and nothing stays in place, so you can't dissect it very easily. So a lot of these questions that you could ask very easily of a cockroach or a mouse, you can't ask very easily of a caterpillar.
Can you freeze it?
Yep, you can freeze it,
Gotcha.
but
Probably screws up all kinds
it
of
does.
things.
Nice.
So we've done cryogenic sectioning
Yeah,
and
yeah.
stuff like that, but it's squishy enough, and even when frozen, it's squishy enough, and the squishiness is different in different places, so that when you do these slices for slides, different parts shear at different rates, and it gets all gooey together. I mean, we've learned a lot by doing these slides, and it's very interesting to see that the muscles seem to pull at places where the body wall folds inwards already, which makes sense when you think about it. But so that kind of you're already working on a fold, a body wall fold, when you start pulling.
But you're not going to pull against an insertion point.
Exactly.
Can we get one more question in before we go? Did you have a question?
Oh, no, I'm just standing so I could hear.
Oh, sorry.
Yep. So.
Can we thank our speaker once more then, please?
Thanks very much.
No problem. And once again, the bill's coming around, so do what you can.
It,
Thank you, John.
Thanks for having me.
at a gut level, what you